Hello, my name is Jeremy Comel. I'm a team/project leader at Yale University under Crystal Pollitt's lab and CEO of Innovative Omics, providing solutions for all your informatics needs for lipidomics and PFAS analysis. Now today I'm going to be talking about FluoroMatch 2.0. This is the newest version of our PFAS software and the only open source PFAS software for non-targeted mass spectrometry. Now, why is it important to look into PFAS? If you look at fluorine, it's the most electronegative atom on the periodic table, and the carbon-fluorine bond is the strongest carbon bond found, and it's not found in nature. It's completely man-made. Now, this carbon-fluorine bond, chemicals containing these carbon fluorines, are very unique in their properties, which makes them very useful. So for example, they're oil and water resistant, so they're found in food packaging, non-stick pans, in furniture such as couches and rugs, where they act as a stain repellent. They also can't be broken down unless you have immense pressure and heat, which makes them good for fluidic devices, for lubricants, etc. Now, all these PFAS can enter the dust, and we can breathe them in, or the air. Some of them are volatile. Furthermore, the water treatment systems don't treat these PFAS because of their unique properties, such as the strength of their bonds and difficulties breaking them down, and therefore they end up in our tap water, in our showers, in our drinking water, all across the US and the world. Now, these carbon fluorine containing chemicals are not isolated to a handful of chemicals. Manufacturers have developed thousands of chemicals. For example, the EPA structural list consists of over 7,000 unique PFAS chemicals, and some of these synthesis pathways, such as historical synthesis pathways and those still employed in China to date, develop non-targeted compounds such as branched isomers. And so the diversity is enormous and unknown. Therefore, we need non-targeted methods for all of our applications, whether we're looking at environmental samples and want to know what the most abundant PFAS are, or those that might cause the most harm to human health, or whether we're looking at consumer products or our product line and want to make sure that we don't have contaminant PFAS species or characterize the different polymers we have. We need non-targeted workflows. So for FluoroMatch, the recommended workflow is to start with your samples. And here you can only require full scan data. It will be used for peak picking. And we concentrate our MSMS efforts on pool samples. We also include extraction blanks, which will be used to remove any background contamination from your lab, extraction procedures, maybe your instrument, to make sure that the PFAS that end up in your final data set are only those from your samples themselves. Now, FluoroMatch supports multiple vendors: Thermo, Waters, Agilent, Bruker, and so SIX. And it supports for MSMS data, auto MSMS data, or data-dependent analysis, as well as any type of intelligent acquisition, which has quadruple selected fragmentation, such as iterative exclusion or rolling exclusion list analysis. It does not currently support all ions. And all you need is the .d files for Agilent, for example. For Agilent, we have tested the software against almost every single QTOF in the product line, and we've found that irrelevant of the QTOF used, that we get comprehensive annotation of the PFAS chemicals in our samples, as well as accurate annotations, and we'll look into that further. Obviously, some of the latest platforms, such as the 6546, will give more high resolution or higher resolution, which can help, again, make sure you have more specificity and accuracy. Further developments using ion mobility, for example, on the Agilent 6560, are under development, but currently not supported. So for FluoroMatch flow, this workflow covers the entire data processing workflow. So for example, all you have to do is drag your files onto this interface, which we show here. You drag the .d files, the MSMS, and the negative mode, full scan, blanks, NEQCs, and then you click Start. And what happens behind the scenes underneath the hood is the software does file conversion, does p-picking using MZMine, does blank filtering, does FluoroMatch annotation, groups by homologous series, and scores those annotations. The other available workflow is our modular workflow. So for example, if you want to use ProFinder or other open source peak picking software such as XCMS or your own MZMine workflow, you can do that. And then you can use FluoroMatch Modular to annotate your feature table with PFAS annotations using your MSMS data files. Also, we have software available for users to develop their own PFAS libraries. So if you have fragmentation data from experiments or from standards for unique PFAS that you want to include in your screening, you can easily generate those libraries and include them in the software and hopefully provide them to the public. Now, FluoroMatch accounts for multiple layers of evidence. It only supports currently liquid chromatography, high-resolution tandem mass spectrometry. And in liquid chromatography, high-resolution tandem mass spectrometry, it takes into account all levels of evidence. So for example, you get your exact mass in your full scans, and it will perform an exact mass library hit to the EPA database. It will also perform mass defect filtering, as fluorine-containing compounds have very unique mass defects, so you can narrow down to what might likely be a PFAS and what might likely not be. It also does homologous series detection, using both the retention time order and the exact mass. So a homologous series is a group of PFAS compounds that only differ in the length of their carbon-fluorine chain. So for example, they may have a sulfonic acid, and then you would call them C2 if they had 2 carbons with 4 or 5 fluorines on the chain. C4 would be 4 CF2 units, C5, etc. And if we plot them by nominal mass and a mass defect, except for this mass defect now we normalize to CF2, then any members of a homologous series will form a straight horizontal line and have the same mass defect. So we can take advantage of that in the software and say, if within 5 ppm, let's say, or 30 ppm, all of these features fall within the same mass defect, and they're separated by 50 Daltons or divisible by 50 Daltons, which is the mass of CF2, then let's all group them into series. And so that's what FluoroMatch does. And so your feature table is nicely organized by different types of PFAS series with evidence for each members of those series. Now, using exact mass and even retention time order alone will not give you a structure. It may suggest that it's a PFAS molecule, but even with exact mass, you won't be able to tell whether it's a PFAS molecule unless you have fragmentation. So fragmentation is very important, and we have multiple layers of fragment evidence that we utilize. So for example, we have fragment screening, where we screen across 777 fragments that we observed based on MSMS spectra from standards. And this is a truly non-targeted approach. So it will look for any of the masses in your fragmentation regardless of the precursor mass, and see if it can annotate, for example, a C2F5 on any of those masses. And if they have fluorines, then it gives you evidence that you may have a PFAS molecule based on the annotated fragmentation. Furthermore, it can be used to discover unknowns. Because it annotates all of your different fragments, if any of them have any of these 777 types of common PFAS fragments, and it also provides the substructures, so the in SMILES format. So you could copy, so for example, this is for PFAS, we see 55 different fragments that were annotated. So obviously this couldn't be done manually, but the software automates this process. And it gives substructures in which these fragments may come from for all 55. And so we could paste all these substructures, as I show some on the left and right, and start to see, if we put these together, that we can form the original molecule, the sulfonic acid with 8 CF2 units. We use this method to discover an unknown PFAS molecule. So in this case, a pentafluorosulfide with a sulfonic acid group, which has been detected before, but in this case with 1 degree of unsaturation, which we haven't found reported in literature. And we are able to determine this new structure in aqueous firefighting foam by using this fragment screening approach and the substructures that were assigned, putting those together. And then we validated it using Agilent's Find by formula, as the 2 sulfur units give a very unique isotopic distribution, as well as the ratio between the carbon-13 peak and the exact mass given the number of fluorines. And so the theoretical and the experimental isotopic pattern matched perfectly, and so we can be confident that this is the right formula. And then we also use the Find by formula approach to assign molecular formula to each of the fragments given the precursor formula, which further gives evidence in this structural annotation. So this shows one example of how FluoroMatch can be used to discover unknowns. 2 other aspects that we use for MSMS are class-based and in-silico-based MSMS. So for many users, especially high-throughput laboratories, there won't be enough time to investigate all the evidence that FluoroMatch gives to discover unknowns. In this case, your lab may just want a list of high-confident annotations, or maybe you want both. Class-based MSMS gives high-confidence annotations by taking standards. We develop the libraries based on standards for each homologous series that we include, and we look at the MSMS, and then develop fragmentation rules, neutral losses and fragment ions, based on 2 or more standards for that homologous series, and develop rules of which fragments must be observed for that compound to be annotated. And we've compared this across standards that were required, targeted methods that use retention time mass to charge libraries and triple quad approaches, as well as manual non-targeted approaches, and we find generally that we have a 100% match, which means these are highly confident annotations that the user can use right away. In silico MS is kind of a hybrid approach where we assign fragments to substructures, and these are tentative annotations. The way that the libraries are generated is first we use MZ annotation, an R package developed by Jason Finch, to filter all of the molecular or structures that are provided in the EPA structural database to those that form M-H adducts. As our fragmentation currently, the rules we've developed are only for M-H adducts, although users can expand those libraries to other types of adducts and positive polarity. After we filtered the 7,000 plus unique PFAS found in the EPA structural database to about 2,589, then we assigned fragments to all 2,589 based on substructures we observe in the SMILES notation. So for example, you can see this structure on the bottom right sulfonic acid with a 6-member ring and 2 CF carbon-fluorine chain attached to that ring. And the way the software would work is it says, okay, if there's a sulfonic acid, based on rules we developed from standards that we acquired MSMS on, we often see a SO3H minus, an SO3 minus, an SO3F minus, and an SO2F minus. And so it will assign those fragments to this structure. Also, we see a carbon-fluorine chain that's 2 carbon-fluorine units long. So let's assign the common fragments to these carbon-fluorine chain of C2F5 minus, CF2 minus, and CF3 minus, and so on and so forth. So it breaks it up into substructures and assigns common fragments, and then screens for those fragments. And if one or more fluorine fragment is found, then it gives a potential structure. And if multiple potential structures exist, it ranks them by the number of fragments it was able to annotate. So you can see here that FluoroMatch takes advantage of a wide array of evidence that we get in our LC-HRM-SMS approaches. We wanted to simplify those results so that users can get some understanding of the confidence assigned for each of their features. And so we developed our own scoring system, which is applied in FluoroMatch, but can also be applied to any non-targeted workflow. So A+ is a placeholder, and that's for those that are confirmed by standards. So in-house retention time, MS and MSMS libraries, very confident in the assignment. That's the most confident you could be. And so those are assigned A+. Not provided by the software, but often users are using a targeted and non-targeted approach. The rest of the A's are those that are also confident annotations. You can be confident in the structure based on this MSMS rule-based approach that we talked about earlier for each homologous series. B's also have MSMS evidence, such as the fragment screening or the in-silico MSMS that we talked about earlier. And so there may be a structure to go off of, but this structure is tentative and needs manual confirmation. C's are those features that fall into series with B's or A's. So they fall into series with something with an MSMS fragmentation match, but they themselves are only exact mass matches. And so we're not even sure they're a PFAS, but we do have a starting structure based on other members of those series to go off of for validation. D's, on the other hand, are solely exact mass matches. They might fall into homologous series with one another, but there's no MSMS evidence to go off of, but they may be PFAS. And E's are those that don't have any evidence related to PFAS and are unlikely to be PFAS, and so can be screened out for further validation. So for example, here's the breakdown of some of the scores for an AFFF sample run on an Agilent 6540. And you can see that right off the bat, you get 74 confident hits. And not only that, but for C+, you get another 151 that fall into series with those 74, as well as some of the B's. So you can say here that right off the bat, you have over 250 annotations that are highly likely that fall across, in this case, 20 or more series. So something that's very powerful to right away get some nice annotations without much validation. Furthermore, you can see another 325 or 9% of the detected features have some type of MSMS evidence of fragment screening, etc. And that will give you a starting point to look into these compounds and determine what they are. Whereas another, about a third, have some type of exact mass evidence, may or may not be PFAS, whereas 39% we can remove right away because they're unlikely to be PFAS. They don't have the right mass defect, they don't have an exact mass match, and no MSMS evidence. It's important to note that we do have a large number of C's, which fall into series with others, so we might expect them to be PFAS, but they have no MSMS evidence, which often means that MSMS was not acquired. So the issue is, in the normal auto-MSMS approach, only the top most abundant ions are selected for fragmentation. So we highly recommend during your data acquisition workflow to apply rolling exclusion lists. It's termed by Agilent, or iterative exclusion, where you inject a sample, such as a pool, maybe a concentrated pool, get the fragmentation, and then re-inject it. And Agilent already has a system where it will automatically generate an exclusion list. And then you can do multiple injections in this manner and increase your coverage. As you can see here, the increase in coverage for Bs, or tentative annotations, is quite stable. And so even after the fourth injection, we may be able to continue to inject the samples and would have gotten even more annotations. Whereas As, which are confident annotations, by the fourth injection, we've nearly covered all of those confident annotations, likely because they're the most abundant, most common PFAS for which we had standards for, and so they'll be selected for first. We also have applied this software to multiple applications, from industrial effluent and wastewater to leachate to numerous individual consumer products. We also want to move forward to biological samples. These biological samples may contain transformation products of PFAS and therefore are very interesting to look into to see how the body might be transforming this PFAS, which is important for screening and determining the health effects of these molecules. And so with that, we'd love for more people to start to apply FluoroMatch and love to hear about your applications. So feel free to contact us. If you have any questions or for information on LC-QTOF or PFAS identification, contact your local Agilent representative. Or if you have any questions related to the informatics approaches for training, research support, and cloud services, feel free to contact me, Jeremy Comel, at innovative-omics.com, or visit our website at innovative-omics.com. And with that, I'd like to thank our contributors. So I'm working mainly out of Crystal Pollitt's lab at Yale University. And then in Crystal Pollitt's lab, we have Paul Stelbin, who's the lead programmer, actually a music major. So you could call this his hobby, but he's programmed most of the software and the new features. Elizabeth Lin is working on gas chromatography, high-resolution mass spectrometry, so that we can extend FluoroMatch to GC as well as LC in the future. And then at University of Florida, another major PI on this project is John Bowden, who is actually the original idea. He said, Jeremy, you've created a software for lipidomics. I think we can start with that framework and start moving into PFAS. And so 2 years later, I've been working on that ever since. Then Juan, Carrie, and Sarah Nason, who've all acquired different LC high-resolution mass spectrometry on different instruments for validation of the software. Sandy Sternberg, if you go to Innovative-Omics, you'll find that there's video tutorials that she recorded for your training purposes. And then Emma Rini, of course, who is the Agilent mentor for the ACT-UR grant mechanism, which has funded this work and has also contributed substantially by networking us with different Agilent users to optimize this workflow, as well as providing insights for the development of this software for Agilent instrumentation. And with that, I'd like to thank you. Again, feel free to contact us.